So, good morning. My name is Madhuvandi, and today I am presenting my internship project titled Smart Factory IoT Monitoring System. This project focuses on applying Internet of Things technology in an industrial environment to improve monitoring and automation. In today's industries, efficiency, safety, and real time decision making are very important. Traditional systems often lack continuous monitoring, which can lead to delay and unexpected failures. So, the main goal of this project is to design a system that can monitor factory conditions continuously, send real time data to the cloud, and allow remote access and control. This project was developed using Arduino simulation tools and cloud platform called ThingsBoard and also PICSimLab. So, introduction to IoT. So, IoT or Internet of Things refers to a network of physical devices that are connected to the internet and can communicate with each other. So, these devices include sensors, microcontrollers, and communication modules that collect real time data from the environment. For example, the sensors can measure temperature, humidity, motion, or light and send the data to the central system. The key advantage of IoT is automation. Instead of humans constantly monitoring systems, devices can automatically collect the data and even take actions based on the conditions. In industrial applications, IoT plays a major role in smart factories. It helps in continuous monitoring of machines, predicting failures, reducing downtime, and improving productivity. It also enables remote monitoring, meaning the system can be accessed from anywhere using the internet. So, IoT makes systems smarter, faster, and more efficient. Next, let's come to the problem statement. In many traditional factory setups, monitoring is mostly done manually. Operators have to physically check machines and environmental conditions, which is time consuming and not always accurate. There is no proper real time visibility of what is happening inside the factory at every moment. Because of this, problems like overheating, equipment failing, or unsafe conditions may not be detected immediately. So, this can lead to production loss, increased maintenance costs, and safety risk. Another issue is that monitoring multiple areas like production lines and warehouses at the same time is difficult. Also, remote monitoring is not possible in such systems. So, there is a clear need for a smart system that can automatically monitor conditions, provide real time updates, and generate alerts when something goes wrong. This project addresses all these problems using IoT technology. System overview. Uh, the system is designed using two nodes. Node 1 is placed in the production lane area and node 2 is placed in the warehouse. Each node is responsible for collecting the data from its respective environment using sensors. So node 1 mainly monitors the machine related parameters like temperature, vibration and machine status. Node 2 focuses on environmental conditions like humidity, light, motion and door status. Both nodes process the data using an Arduino microcontroller. Then the data is transmitted to the cloud using an internet-based network and MQTT protocol. The cloud platform used here is ThingsBoard, which stores the data and displays it on dashboards. Users can view this data in real time and also send commands back to the system. So this architecture allows distributed monitoring with centralized control. So use cases. This system can be applied in multiple real world scenarios. First, in machine monitoring. The system continuously tracks whether machines are running or not, along with parameters like temperatures and vibration. Next, environmental monitoring. In the warehouse, temperature and humidity are monitored to ensure proper storage conditions. Third is fault detection. If any parameter exceeds a predefined threshold, the system generates alerts immediately. For example, if temperature becomes too high, a warning is shown on the dashboard. Another important use case is automation. In the warehouse, if humidity becomes too high, the system automatically activates ventilation. It also supports remote control. Users can control devices like relays directly from the dashboard. All these use cases help improve efficiency, reduce manual work, and ensure safety. Next, a block diagram. First, here we have sensors, microcontroller, which is the Arduino board, Ethernet module, cloud, which is the ThingsBoard, dashboard, and user monitoring. So basically, at the first stage, we have sensors. These sensors collect data such as temperature, humidity, motion, light, and vibration. Next, this data is sent to the Arduino microcontroller, which processes the raw signals and converts them into meaningful values. Next, the process data is transmitted to the Ethernet module and MQTT protocol. MQTT is a lightweight communication protocol that is very suitable for IoT applications because it uses less bandwidth. Next, the data reaches the ThingsBoard. So it is a cloud platform where data is stored and analyzed. Next, finally, it is displayed in the dashboard using graphs, gauges, and indicators. Users can monitor this system in real time and also send control commands back to back into the devices. So the entire system works in a cycle of sensing, processing, transmitting, and visualizing the data. So next, so tools and software used. So here we use PICSimLab, which is used for simulation. Like we can simulate it for testing and circuit designs. Next, Arduino IDE, which is a programming platform for microcontroller development. Next, ThingsBoard, a cloud platform for data management and visualization. So, embedded C, programming language for sensor integration. Next, MQTT layer, protocol, which is a lightweight messaging protocol to IoT communication. Next, for example, if we take uh, a data and if we try to use it for communication, we can use MQTT protocol more. Next, node 1 production line. So now I will explain node 1, which is used for production line monitoring. So this node focuses on machine health and operational conditions. It uses multiple sensors. The DHT22 sensor measures air temperature and humidity around the machine. Next, LM35 sensor measures the machine surface temperature with high accuracy. Next, vibration sensor is used to detect abnormal machine vibrations, which can indicate mechanical issues. Next, a push button is used to simulate machine on or off status. All these values are read every 5 seconds and sent to the cloud. One important concept here is real-time monitoring. Operators can continuously see machine conditions without physically being present. Another key concept is fault detection. For example, if machine temperature exceeds a critical level, the system highlights it immediately. There is also a remote control functionality. Using the dashboard, the user can send an RPC command to turn off the machine relay, preventing damage. Additionally, LED indicators are used for status, green indicators normal operation, yellow indicators used for warning, red indicators used for critical condition. This node helps in reducing downtime, improving maintenance, and increasing the production efficiency. Next, node 2 warehouse. So node 2 is responsible for warehouse monitoring and environmental control. It uses sensors to track storage conditions and security. The DHT22 sensor measures temperature and humidity. The LDR sensor measures light intensity. Based on this, the system determines whether the warehouse is dark. The PIR sensor detects motion, which is useful for security monitoring. A reed switch is used to detect whether the warehouse door is open or closed. Next, one of the most important features here is automatic control, specifically auto ventilation. If humidity exceeds 85%, the system automatically turns on the ventilation relay. This prevents damage to stored products. Another important concept is event-based monitoring. Example, when motion is detected, the system keeps the signal active for a few seconds to avoid false triggers. This mode also supports remote override. The user can manually control the ventilation system through dashboard even if automation is active. So overall, Node 2 ensures product safety, maintains proper environmental conditions, and improves warehouse security. Next, implementation using the ThingsBoard platform. Okay, first is device connection. Next is data transmission. Next, dashboard creation and alert configuration. So ThingsBoard is a cloud platform used in this project. It is an important one. So first, devices are connected to the ThingsBoard using MQTT protocol. Each device has a unique access token for authentication. Once connected, devices send telemetry data to the server in JSON format. The platform stores this data and allows real-time visualization. Dashboards are created using widgets such as gauges, charts, and indicators. For example, temperature can be shown using a gauge, humidity using chart, and mission status using a LED indicator. Another important feature is the rule engine. The rule engine checks conditions like threshold limits. For example, if temperature exceeds 35 degrees Celsius, it generates a critical alarm. Next, this allows sending commands from dashboard to the device. For example, turning on or off a relay. So ThingsBoard is not just for monitoring but also for control and automation. It acts as the brain of the system. Next, future scope. This project can be further improved in many ways. More sensors can be added, such as gas sensors or pressure sensors, for advanced monitoring. Artificial intelligence and machine learning can be integrated for predictive maintenance. This means the system can predict failures before they occur. A mobile application can be developed so no users can monitor the system from their phones, like more users. The system can also be expanded to support multiple nodes across a large factory. Another improvement is automation, where more actions can be automatically controlled without human intervention. Security features like data encryption can also be added. So this project has a lot of potential for future development. Next is results. So now coming to this part, the system was successfully implemented using simulation. Both nodes were able to send data to the cloud continuously without failure. Real-time monitoring was achieved. With data updating every few seconds, the dashboard displayed all parameters clearly using visual elements like graphs and gauges. The system responded quickly to the changes. For example, when temperature is increased, it was immediately reflected on the dashboard. Automatic actions like ventilation were triggered correctly when conditions were met. Next, overall, the system proved to be a reliable and efficient response. Next, conclusion. So, to conclude, this project successfully demonstrates the use of IoT in industrial monitoring. It improves real-time visibility into factory operations, which helps in better decision making. It reduces the manual effort and minimizes the human errors. The system is scalable, meaning it can be expanded easily. It is also cost effective because it uses simple hardware and cloud-based solutions. By integrating monitoring, automation, and remote control, the system improves efficiency, safety, and reliability. So, this project shows how modern technologies like IoT can transform traditional industries into smart factories. So, thank you. And if you have any questions, you can post in the comment section. So, I'll next show the code implementation. This is node 1. So, this node 1, we have different files, which is node 1, next sensor, network, telemetry file, activator file, sensor manager, and configuration file. So basically, so node 1 has all the first initializations and include all the libraries which are need to be included is first given. You can see. So here the server is MQTT ThingsBoard and the port is 1883. This is my access token. This is the client ID. Next, these are the configuration pin configurations, and this is the baud rate at which this program is performing. Next, you can see sensor data, how the sensor is read, and here millis function is used for timer calculation. It is inbuilt in Arduino itself. So activators, telemetry, all are called here. Next, network. First, we will define the variables in the network.h. So these are the variables and it will be included in CPP. And if the MQTT is connected, it will print connect and topic RPC request will be subscribed. Otherwise, MQTT will be failed. Next, you will do the Ethernet connection, and this is for MQTT connection code. Next, telemetry. Here, variables is given, this telemetry. And here we will read the data of temperature, humidity, and LM35 temperature, and we will display it here. It is printed. Next, activators. This is the activators file which have the initializations, and it will be included in this activator files. So where green, red, yellow will be set as output with relay. Defaultly red will be high. So basically it means that it is not connected to the ThingsBoard. Next, after that, when MQTT is not connected, I told you that red is high. After connection, it will turn to green. So green is high. If any sensor error is there, and then we will have yellow as high. Next, sensor managers variables are declared here. Next, sensor manager. So here it is vibration is red and LM35 sensor is red and sensors are also red here. This is the configuration file which have initial configurations, and this is the RPC file. You can see. Next, is this the node 1 implementation? So yeah, this is the node 1 implementation. I think then yeah, this is the node 1 implementation. So which will have PIR sensor, LDR sensor, DHT22, ventilation relay, door switch, etc. This is the node 2 which will have machine control, relay status, vibration sensors, DHT22 and LM35. So next I will show the node 2 code. Sorry, this is node 2 and this is node 1. Yeah. So yeah, warehouse. Okay, warehouse uses the DHT22 LDR PIR sensors, right? So this is the node 2 and this is node 1. Yeah, node 1, this is the node 1. So node 1 has vibration sensors, DHT22, LM35, machine control, relay status, etc. Node 2 has LDR, PIR, and this is the Ethernet module, DHT22, etc. So I'll first explain the node 2 code now. So yeah, this is the node 2 code. Similar to that, same things are there, but we will change the sensors alone. Same code is there for sensor manager node, activators, network, sensors, and telemetry, RPCs. The same code is there and same initialization is there. So I already connected it. So it shows green color. So this is the node 1 implementation. Now I'm showing the node 1 implementation of PICSimLab. So this is the virtual terminal. This is the THT22 sensor which is used to read the temperature. If I change the temperature, it will also change in the Things cloud because I already connected it in the Things cloud. Next, LM35. This is also a sensor which is used. Next, vibration sensor. Next, machine control. Next, this is the Ethernet module and relay status, and it shows green now because I connected it to the ThingsBoard already just by running this. I mean, loading it in this uh, Arduino board. You can send the clouds, I mean data to the cloud using Ethernet module. Next, this is Node 2 implementation, which has virtual terminal, Ethernet, LDR sensor, uh, potentiometer, which is used as vibration sensor. Sorry, yes, vibration sensor. Next, DHT22, PIR sensor. Next, this is used for checking whether it is connected to the ThingsBoard. Next, door switch and ventilation relay. So it's already connected. So if I change the values, it will also get changed, reflected in my ThingsBoard. So I'll show you the ThingsBoard implementation now. So yeah, here this I go to the dashboard. Now first I'll go to the devices. So devices, this is the production line node 1. But if I go to the latest telemetry, you can see the values. For humidity, I got 54, LM35 120, machine status 1, relay status 1, sensor error 0, temperature, vibration as 59 and 644. Next, I go to the warehouse. Warehouse also, I will get the latest telemetry. For door open, humidity is dark, LDR value, motion detected, relay status, sensor error, and temperature. Now I'll go to the dashboards. So dashboard is nothing but the same, these data is represented visually. So you can see this. This is the node 1 dashboard. So I'll explain you this. This node 1 dashboard is similar to that of node 2 dashboard also. And so what this is the temperature gauge. First, this is the temperature gauge. This shows the surrounding air temperature near the production machine. So currently it is around things 50s. So it falls in the red zone. So it tells that it needs immediate action. So here, okay, it is 60. Shows 60 here, I think. It shows like okay. So it is around the range 60. Next, humidity. And humidity gauge shows the moisture level in that. It is around 55 percentage, which is okay. Next, time series chart. This graph shows how temperature changes over the time. It helps in analyzing the trends rather than just current values. If the temperature is gradually increasing, it indicates a potential issue before it becomes critical. Next, humidity I also visualized using this range bar. So I did two of this. Next, relay state. Uh, Relay state, which controls the machine power, is currently on, meaning the machine is powered. Using the dashboard, this relay can be turned off remotely in case of emergency. Next, mission status. On the right side, we have mission status indicator. It is currently showing on, which means the machine is running. Next, sensor error. This indicates shows whether there is an issue with the sensors. Right now, it is off, means sensor is working correctly. Next, time series table. It shows recorded values within the timestamps for temperature, humidity, LM35, and machine status. Okay, relay and sensor error, vibration, everything. So it is useful for historical analysis and troubleshooting. Next, alarms. So only one alarm I created. Like I created everything alarms, but now only the temperature is critical. So only one alarm is raised. Okay. So yeah. Next is node 2. It is also mostly similar to node 1 only. First, we have the humidity here. This humidity gauge shows the current humidity level, which is around 27 now. It is not in critical stage. Next, so the color is not up to here. It's okay. So this is the temperature gauge. Uh, it is around 40 degrees Celsius. Okay, 40 degrees Celsius. Next, motion indicator. It shows that it is off, meaning no motion is detected. It is connected to the PIR sensor. Next, door status is the door indicator. It is currently showing that door is open. Next, switch control. Uh, Here we have a manual switch control. This allows the users to manually turn on or off the ventilation system. Next, again the same time series chart, time series table. Next, it displays all the values. Next, warehouse dark indicator. It is based on LDR sensor. Right now it is off, meaning there is enough light. Next, delayed state. So ventilation system is active. Next, only one, here also one alarm, because we have recorded that, wait, it's dark alarm. Yeah, okay. So now the current stage is dark, so it gives a warning. It's not a critical one. It just gives warning. So wait, this is a note to write. Okay, so after increasing the humidity, I got the alarm for critical. So actually, here you saw that I increased the humidity to a large level, because of which I got another alarm, which is critical alarm. Not like it's dark alarm. It is just a warning, but here I got critical alarm. Also see that temperature also changed, the graphs also changed. So yeah, so by changing the values, this gets changed. Next dashboard is smart factory. So it basically displays the overall all the historical values of both the production lines. Also, I also gave the time series chart for temperature for both of the nodes. You can see how it is varied, and also production line. All the details are here for both production line and warehouse. So this is the project implementation. So thank you.